The proportion is considered a measure of center when dealing with a variable that has a binary outcome. The proportion is usually defined as the number of observations within a process or population that meet a certain criteria, divided by the total number of objects assessed. Just like with the mean, we can estimate the proportion based on a sample. The natural statistic for estimating pi is given on the slide. This is just the sample proportion. It is determined by looking at the number of objects that meet the requirement divided by the sample size. Inference on a proportion is based on a random sample of size n selected from the population. Let's look at some details. Since pi is a proportion, we know that it can take on any value between 0 and 1. Just as what we saw with the mean, the sample proportion will change from sample to sample. As an example, let's assume that a sample is drawn of size 5. Usually we utilize a proportion as the measure of center when the data are binary. In other words, when there are only two possible outcomes. We will set one of the outcomes as a success, denoted by S, and the other as a failure, denoted by F. The success is usually defined as the outcome of interest. If the variable is considered capital X, then a success yields x equal to 1, and a failure yields x equal to 0. So based on the example given in the slide, we have 3 successes and 2 failures. This means that the sample proportion will be 3 out of 5, or 0.6. Just as with the sample mean, we get a distribution for the sample proportion. This distribution is centered at pi. The properties of the sampling distribution are given in the slide. As long as both criteria are met, we get the mean and variance of the sampling distribution as given on the slide. We will use this information to create a test statistic in order to test hypotheses and create confidence intervals for pi. Let's first look at the test statistic. When we deal with two proportions, we are normally dealing with either the difference or the ratio. At this point, we will focus on the difference. Let's look at the sampling distribution of the difference. If we have two random variables that come from a binomial populations, the mean of the difference is just the difference of the sample proportions. The variance of the difference is just the sum of the sample variances for each sample proportion. Now, knowing this and that the proportions are measures of center, we can create the probability statement that leads us to the acceptance region. The statistic in the probability statement on the slide is of the form of the sample mean of the difference in proportions divided by the sample standard deviation of the difference in proportions. Now, based on this probability statement, we can get the acceptance region as given in the slide. Now we can create the confidence interval from it. After substituting the sample proportions into their respective variances and then rearranging everything, we get the equation in the slide for a confidence interval for the differences in proportions. Let's try an example. Here are the results of a study taken over 5 years. It is a randomized study testing whether or not regular intake of aspirin reduces heart attacks. Let's use this example to create a 95% confidence interval for the comparison of the proportion that have heart attacks between the placebo and the aspirin. Here are the assumptions. Notice that since each of the successes and failures are greater than 10, we can use the z-test. Now we can determine the critical probability as 0.975 and then get the critical value as 1.96. The lower bound calculation is given in the slide. The lower bound is 0.0047. The upper bound calculation is given in the slide. The upper bound is 0.0107. Now let's look at the interpretation. The interpretation is as follows. We are 95% confident that the true difference in proportions is between 0.0047 and 0.107. Now let's look at a two-sample hypothesis test for proportions. We will assume that we are still working with a difference in proportions, so we can formally state the null hypothesis as either pi sub 1 equals pi sub 2, or the difference in the pi sub i's is equal to 0. Now we can use the acceptance region given here to get the test statistic. The test statistic is given in the slide in its general form. We still need to make sure that the assumptions that are in the slide are true. Now, how do we change things if delta is 0? So if the delta is 0, then we assume that the proportions are equal. This means that the denominator simplifies to what you see in the slide. Now, what do we do with pi? So if we assume equality, we need to estimate pi. We will do this by combining the two samples as seen in the slide. This occurs because we now assume instead of having two distributions, we have one binomial distributions with pi equal to pi and n equal to n1 plus n2. So now our test statistic becomes what you see in the slide. Let's try an example. So we are basically comparing the proportion of rural adult residents to urban adult residents who believe that the speed limit should be increased. We want to see if there is a difference in terms of the proportion in favor. You can find the solutions to this problem in a file called Example2 Two-Sample Proportions. Let's look at the conclusions. Since the p-value is less than alpha, we decide to reject the null hypothesis of equality. The real-world answer here is that there is indeed a difference between the proportion of adult residents that want to increase the speed limit between urban and rural areas.